I think it's time we try out a new gear train. And so our green gear is turning our blue gear, which is turning our orange gear. And let's call our biggest gear here gear Z. And let's say it has 36 teeth. And then our middle gear we'll call gear Y, and let's say it has 18 teeth. And then our gear on the left, our driver gear, which is our smallest gear, let's call it gear X, and let's say it has 6 teeth. And I want to use this new gear train to focus on rotational speed and torque. And so gear X will be our driver gear, and let's say our driver gear has a torque of 30 foot-pounds. And let's say we need to figure out what the torque for gear Y is and the torque for gear Z is. And let's say the rotational speed for gear X is also 30, just so we can compare our torque to our rotational speed side by side. And omega's units deals in RPM, or rotations per minute. And we'll use that to figure out our rotational speed for gear Y and our omega Z. And let's start with torque for gear Y. And to solve for this, I'm going to use what I'm given, which is my number of teeth. And we know that our number of teeth output divided by our number of teeth input is our gear ratio formula for number of teeth. But I'm going to set that equal to our torque. And so we'll say equals our torque output divided by our torque input. And so let's draw out our proportions for ourselves. We can say that our number of teeth output, which goes on top, our output is our gear Y, and it has 18 teeth. And on bottom goes our number of teeth input, while our driver gear is gear X, which has 6 teeth. And that is equal to our torque output divided by our torque input. Well, our torque input is gear X, which is 30 foot-pounds. And our torque input for gear Y, we don't know, which is kind of the point here, so I'm just going to put torque Y on top. And to figure out torque Y, we can just cross multiply and divide. And so we can say 18 teeth times 30 foot-pounds divided by 6 teeth. Well, teeth clearly cancels out. And so what are we left with? Well, we're left with a unit of foot-pounds, and that makes sense because we're solving for torque of gear Y. Well, 18 divided by 6 is 3, and 3 times 30 is 90 foot-pounds. And of course, if you don't trust my math, you're more than welcome to pull out your handy-dandy calculator. We can plug this in here. We can say 18 times 30 on top, and then 6 on bottom, and we get 90. And of course we do, because math. And let's compare our torque Y to our rotational speed for gear Y. And to solve for this, I'm going to again use my number of teeth ratio, our in-out divided by our number of teeth input. And I'm going to set that equal to our rotational speed ratio. But if you notice, omega input is on top and omega output is on bottom. This is actually inversed to all the other ratios, and it's very important that you see that for omega we put input on top and we put output on bottom. And let's draw out our proportions for ourselves. And we're still using our gear ratio from X to Y, and so our number of teeth output hasn't changed. 6 teeth still goes on bottom, and 18 teeth still goes on top. What changes here is now we put our output on bottom. And so we put our omega Y on bottom. And we put our input rotation on top. So to solve for omega Y, we can just cross multiply and divide. We can say 6 teeth times 30 divided by 18 teeth. And we get 10 rotations per minute. And so let's pause for a second and let's think about that. We had the same numerical value for our torque as we did for our RPM for our driver gear. And as we went to a bigger gear, our torque went up, but our rotational speed went down. But if you think about that for a second, that makes way too much sense. Torque is based on a force multiplied by a radial distance. And so if we make our radial distance 3 times bigger, it makes sense that our torque would also become 3 times bigger. But the rotational speed would go down. Think about it for a second. For gear Y to spin 1 time through, 18 teeth has to go by. Well, if 18 teeth goes by in gear X, that means gear X spun 3 times, 6, 12, 18. And so for every 3 times gear X spins, gear Y will spin once. And so if gear X spins 30 rotations per minute, then gear Y would spin 10 rotations per minute. And so hopefully that makes way too much sense, and now you understand why the rotational speed ratio is inverse. It's in over out versus the other 3, which are out over in. But with that, let's go ahead and solve for our torque and our rotational speed for gear Z. And actually for gear Z, I want to show you that we don't have to use our number of teeth ratio to solve for all the others. We can use any one of these ratios to solve for any of the others. So for example, to calculate our torque for gear Z, we can use the gear ratio itself. And so let's do that. Let's say to solve for our torque of gear Z, we are going to use our gear ratio itself is equal to our torque output divided by our torque input. And so what is our gear ratio from gear X to gear Z? Well, if we look, gear Z has 36 teeth and gear X has 6 teeth. And of course, teeth cancels out, and so we get a gear ratio from X to Z of 36 divided by 6, which is of course 6. And so we can plug that in right here. We can say 6 equals our torque output divided by our torque input. Well, we still know our torque input is gear X, which is 30 foot-pounds. And we don't know the torque for gear Z, so we'll just leave that as torque Z on top. And I'm going to put 6 over 1, so I can make this a simple cross multiply and divide. And what do we get? We get 6 times 30 divided by 1. Well, 6 times 30 is, of course, 180, and 180 divided by 1 is still 180. So we can say the torque for gear Z is 180 foot-pounds. And again, hopefully that makes way too much sense. If our gear got twice as big, then of course the radial distance would be twice as big. Therefore, the torque would be twice as big. But the point I want to get across to you is that we can use any of these ratios to solve for another. So for example, I can use my torque to solve for my rotational speed of gear Z. And so I'm going to say to solve for gear Z, I'm going to use my torque output divided by my torque input. And I'm going to set that equal to my rotational speed ratio, which is, of course, input divided by output. It's very important that you remember that. And of course, the torque output would be the torque of gear Z, which we just got was 180 foot-pounds. Versus the torque input, well, I'm going to continue to use torque X as our driver gear or our input. And so I'll say, well, that has a torque of 30 foot-pounds. Versus our rotational speed input, which we said was 30 RPM, over our rotational speed of our output, which is gear Z, which we do not know. So we'll just leave that as omega Z. And so to figure this out, all we have to do is cross multiply and divide. So we can just pull out our handy dandy calculator. And so we'll say 30 times 30 on top divided by 180 foot-pounds. And what do we get? We get a rotational speed for gear Z is 5 RPM. And so solving for speed and torque is really no different than solving for diameter or number of teeth or the gear ratio itself. But the thing you got to remember is that for rotational speed, as your gears get bigger, your speed gets smaller, which is of course why this ratio is flipped.